Vamos a tener una conferencia plenaria, keynote, que va a ser brindada por Bill Nichols del Software Engineering Institute. La conferencia tiene como título una frase de Watch Humphrey: "If you don't know where you are, a map won't help". Ese es el título de la charla. Los dejo con el orador Bill Nichols.
So I will speak in English. I've tried to structure the presentation so that non-native speakers can follow. But please come and tell me afterward how well I've succeeded. What I want to talk about is quality. Quality in software, what it means to me personally, and what we at the SEI have been doing to push the idea of quality for the consumers and for the developers. The metaphor is the quality journey. My own personal journeys have taken me all over the world. Montevideo today, but I've worked in Tokyo, in Fukuoka, Japan, in Istanbul, in Johannesburg, in Cape Town, in the UK. Quality is worldwide. Oh, this is the way. Now, I'll start off with the observation of the obvious. Software is everywhere today. Software allows us to do remarkable things that were just unimaginable a generation ago. They're on our televisions. They're in our ovens. Of course, they're in our phones. But they don't always work. How many of you have had this? I got rid of my BlackBerry phone when it crashed. While I was received an incoming call while making an outgoing call. My outgoing call was to find the late taxi for the airplane. Well, I almost rebooted that computer the hard way. I almost gave it a good kick. So that was the end of the BlackBerry for me. I now have an iPhone and I'm much happier. But you know, it doesn't work perfectly either. It works a lot better, but it's still not perfect. I have on my desk one of these. How many of you still have one of these? No? You do? Yeah. Yeah. You know why I have this? It really does work, by the way. It really does work. I have to have an adapter to plug it into the digital network. This phone is older than me. Not by much. But it still works. I wanted to be reminded that we once knew how to make things that would just work and keep on working. Well, I'm going to come back to a couple of repeating themes. I'm going to talk a little bit about areas of software where we really can't tolerate defects. For example, in medical devices. I'll talk a little bit about the space program, coming back to the journey metaphor. Is anyone familiar with the Therac 25? Yeah, it's a case study. It's very well known. My background is in physics, so I actually learned about this in a nuclear physics course, not in a software course. The 25 MeV Gamma Knife, remarkable machine. It allows the doctors to operate and remove tumors without otherwise physically damaging the patient. It was really remarkable, except there were some problems. In this particular case, several patients were killed, several others were seriously injured because of a software defect. Well, it's an oversimplification to say a single software defect. There were a lot of contributing causes. But the proximate cause was a race condition, very common race condition, keyboard problem. If you hit the keys a little too quickly, mistyped, hit the backspace, re-entered, it did not take the new value, and several patients received very severe overdoses. A lot of other things went into the engineering of that system. But software defects have very real implications. Now, the problems in software are pervasive. We can actually measure defects in software in defects per thousands of lines of code. Now, let's put this in perspective. Lots and lots of industry data says your typical applications out in the field average somewhere around maybe 5 defects per 1,000 lines of code. Maybe. That's very rough. It varies quite a bit depending on your programming language, environment, etc. Very good ones are down to 1 or 2. Now let's do a little math. Previous release of Windows would have been maybe 50 million lines of code. Okay, how many defects is that? Tens of thousands of defects. That's in some of the best product out there. Ever heard of Jerry Weinberg? Jerry Weinberg was one of that group of geniuses that came out of IBM in the 60s and 70s, just a remarkable group of people. His second law, you do have woodpeckers in South America, I checked. I wanted to make sure you recognized. Second law, if builders built software, if builders built buildings the way programmers built software, the first woodpecker that came along would destroy civilization. Now, this is an exaggeration, perhaps, but maybe not so much. Consider the kinds of problems we have in computers today. I remember back in the 90s, we would be running software on isolated machines. Guess what happened in the 2000s? They plugged those into the internet. Now, all of a sudden, there are all sorts of new exposures. Defects in those computers can propagate onto the network. The world is very connected, and we are more and more reliant upon software that actually works. And as one wag put it, with software, failure isn't an option, it's a feature. So, why does software fail? There's a school of thought that says defects are just an inherent property of software. It's very complex. It's the most complex thing that humans have ever done. Software defects are just going to happen. There have been groups that have been trying to encode this into law to protect themselves from some of the product liabilities. But what if the software defects are really a consequence of our development methods? Now, humans are not perfect. We know humans are going to make mistakes. That's part of being human. But there are still artifacts out there that have been made that have lasted a long time with few or no defects. How did they do it? What did we forget along the way? Or what could we do differently in software? Is software really that different, fundamentally? So this is a rhetorical question. But if we can put a man on the moon, actually our grandfathers, would have been my grandfathers, some of your great-grandfathers, put a man on the moon. Why do we still have problems getting a reliable iPhone app? Why indeed? But I'm going to use the space metaphor as the journey. I'm going to look at some of the examples along the way, come back to the space program and medical devices, and talk about the techniques that we can apply or the stages we can go through to improve the quality of software. And I chose the space because in spaceflight, failure is not an option. Mistakes are fatal, much like the medical device industry. There we go. So let's begin at the beginning of that journey. This is before my memory. I was alive at the time, but I don't remember it. John Kennedy at Rice University gave a very famous speech, and we can use this as an example of how you give a proper set of objectives, very high-level objectives. What do you want to accomplish? You want to go to the moon. We're going to send a giant rocket fitted together with precision better than the finest watch. There's a quality goal. Carrying all the equipment for propulsion, guidance, control, communications, food and survival. He's implicit in there that the men are going to be aboard this ship. And then return it safely to the Earth. Another quality goal. And do it before the decade is out. A schedule goal. How did they do it? They actually achieved that mission, but it didn't happen all at once. So when you're going to go on a journey, you need a guide. That's not who I meant. There he is. Actually, he does look a little like the other guy, doesn't he? Watts Humphrey. Watts Humphrey is part of the reason I went to the SCI. Back in the early 2000s, I was working on a development project at our laboratory. I worked in a nuclear lab developing analytic software for nuclear reactors. And we had the SCI come in and help us with our project planning and our quality. And I really got very excited about the type of work. And when the opportunity came to join the SCI and work with Watts, I couldn't pass it up. Now, Watts is considered by many a father of software quality. There's an institute in India named for him. The IEEE Quality Medal is named for Watts Humphrey. And he, in one of his papers, coined the term the process revolution. The process revolution, in his mind, he was thinking in terms of scientific method, of applying real engineering approaches. Most people don't know this, but Watts actually worked for the physicist Enrico Fermi when he was a student. Now, to mature software engineering, we must learn from history. To learn from history, we must refine what we do, we must define what we do, and when we develop software and how we do it. He said we must define how we do our work. If we don't define our work, we can't do it repeatedly. Then, we must produce a process specification and measure the work. Define and measure. Then you have the beginning of the basis for doing things reliably. And that is why the process revolution is so important. So, the first step along the way. There are a number of steps that people and organizations typically go through as they develop higher quality processes and projects. A first step is often test and fix. It's trial and error. It's a very human way to move in a direction when you're doing something that's unfamiliar. You'll try something out and see how it works. If that doesn't work, you'll try something differently. So if we go back to the beginning of spaceflight, here's what trial and error looked like a little bit. That didn't work. I kind of get the idea of what they're trying to do, but I don't know why they thought this would work. Any of you remember Wile E. Coyote from the Warner Brothers cartoons? This next guy reminds me of Wile E. Coyote. That didn't work. Let's try going a little higher. Oh, okay. You know, the problem was we weren't high enough. So, this time, for sure. Maybe not. Okay, that's an exaggeration. That is an exaggerated trial and error. But to make the point, there are problems with the test and fix approach. Let me list some of them. First of all, test is very light. To test something, what do you have to do? You have to have something to test. That means you must have already gone to the effort of building it. So you saw a couple examples of testing to destruction. If you test something and it's not right, you might have to start over completely. Relying on testing can be a very expensive way to make progress. There are other problems. In the software world, we have lots of data that says testing is seldom more than 50% effective. That's in any specific testing phase. It's very hard to do much better than that. And there are reasons it's hard. For one of them, defects often mask other defects. When I was doing a lot of testing at the lab, very often we would fix a problem, and then all sorts of other things started to break. What was going on? Well, until something went through a path, sometimes these other paths were blocked. But how many times have you fixed a bug, a seemingly trivial bug, and something else broke? It happens because you can change program state in other ways. Those other ways were masking other potential defects. It happened to me again and again and again. Some tests are difficult to actually execute. How do you execute a test for that race condition in the THEREC? I mean, think about what you have to do when you're running human interface tests. You're reading a protocol, right? You are trying very carefully to follow the protocol. It's unlikely you're even going to get that speed. That is unlikely to happen until you get people in the field who have acquired the dexterity and the practice to type fast enough. So some tests are going to be difficult. Now, here's the real killer. Relying on testing. Now, I'm not saying testing isn't important. Testing is an absolutely critical part of the process. But relying on testing to remove volumes of defects is not economically viable. You have to fix every defect you find. And before you fix it, you have to actually find it. Testing identifies a symptom. If you're lucky, the program crashes. If you're unlucky, you get the wrong result. They can be very far removed. That can be a very time-consuming process, very expensive. So for volumes of defects, testing is not effective. What we have found, we have a lot of data that suggests test and fix takes longer when you've actually measured. But there are other techniques. Building it right the first time, building it right is faster. So where do you go from here? The process is a human process. It's a learning process. So we have to go one step at a time. There is lots of good documentation on how people learn. You have to reach a step in your process, master it, and then learn something else. Often, when you get to that step, you learn more about what you need to go to the next step. And a reasonable second step is to inspect the product before you put it in the test. Try to find those defects directly. So let's take a look at this. Michael Fagan. Have you heard of Michael Fagan? There is a wonderful story about Michael when he was a young engineer at IBM. Michael was not a software engineer by training. He came out of the hardware space. And he went to his boss, Al, and said, you know, I have an idea. I'm paraphrasing. He presented Al with an idea. In the hardware world, they were using inspection techniques to find a lot of defects in their processes and their products before they went into production. And it was really effective. And he tried to make the cell. But, okay, that worked in hardware. That would never work in software. So Al was unimpressed. He dismissed Mike despite the protestations, but what did Michael do? He went ahead and did it anyway. He came back 1 year later. This time he brought data. What kind of data do you think he had? He had data on defects found in inspections. He had data on how much time they were spending in find and fix time in their testing. Al thought this data was so compelling, they rolled out using the inspection process across that lab and all of IBM. Michael Fagan is the word in inspections. When you talk about inspections, you talk about Fagan inspections. All sorts of other variants today, but everyone who does inspections knows about Michael Fagan. Next logical step. So let's describe a little bit about what makes a Fagan inspection work. A Fagan inspection is formal. It's not a desk check or a casual review. There's a lot of formality. You'll have roles, you'll have inspector roles, you'll have meetings, you'll have checklists involved in the inspection. That formality is the way they were taught to do it in the hardware world. Now you can apply inspections to requirements. A little harder. You can do it in design, obviously code. You can inspect test cases. So you can inspect each of these products before you put your product into test, and you find the defects directly. Now, you can find depending on your domain. We've seen numbers that vary from 50 to 90%. Sometimes they aren't quite as good as 50%. But good inspection should be able to get 50% of the defects at any given time, and you can get maybe as many as 90% altogether just by inspecting the products at different times in the stage. So think about that. Whoop. Went the wrong way with that. Okay. So think about being able to trap maybe 60% of your defects. You find them directly. You find the defects directly. When you see a bug, you know exactly what it is. You can go and fix it. You don't have to go on a treasure hunt. You don't have to go on an Easter egg hunt looking for the source of that problem. IBM had some remarkable data. For each hour of inspection on a severe defect, they saved 22 hours of test and 80 hours of rework. That's 100 to 1 savings. That's for the severe defects. What about the not severe? Even for those, they were finding paybacks of 2 to 1. How can you afford not to do it? If you've got a product that's going to be in the field for any length of time, that rework is a very important number. Now, I can't talk about the specific companies, but I have some specific examples in mind today of companies that have come to us with some software quality problems. They had devices in the field that they were supporting. They were spending so much time in rework fixing the bugs in their fielded product that they had 0 new product in 18 months. They simply didn't have the capacity to do new product because they were stuck here. And just by doing some of the early parts of this, they were able to turn that around. Now, this suggests that you should be able to increase cycle time. When we talk about agility, about the ability to deliver product in a timely manner, it's one of those cases where slowing down a little, slowing down initially, speeds you up. Dramatically reduces the maintenance costs. And by the way, when you go through the inspection process, you really do spread knowledge. One of the things that's constantly amazed me going through the inspection meetings, well, a couple of things. One of them is we always find more defects in the meetings than any of us found individually. We always find new ones. And we're always learning from each other. The more experienced people they can share the experiences they've had, their observations from all of the work they've done in this product. Some of the newer people can share some of the newer techniques they've learned. But you know what? It's not enough. It gets you a long way, but it doesn't solve all the problems. In fact, it uncovers new problems. You realize that you can fix the product after you've put in these injected these defects, but you're still injecting defects. You haven't really fixed the process that injects them, and that's one of the insights that the hardware world came to, manufacturing came to in the middle of the last century. Inspection can only be applied when you have an inspectable artifact. Well, you have to build the code, right? Anyone put it in to compile without the code? We're starting to push the bounds with some newer, higher generation languages, but you have to have something to inspect. So if you don't do formal requirements documents or formal design, you cannot inspect them. You can only find recognizable defects. You have to know what wrong looks like. So you have to have some standards, you have to have some idea of what is right and what is wrong, or you can't really do an inspection. That's just saying, though, that you have to have this under intellectual control. Another problem is conducting inspections. How many of you have had a product go through a peer review? Yes, some of you. One of the problems that you have to overcome is if I've produced a product, I feel a sense of ownership. How do you think I feel if someone starts criticizing the product? Yeah, it can be very difficult. So you have to be very careful from a people standpoint how you handle these inspections. You have to be clear that you are inspecting a product, not a person. And I've seen many inspection programs go bad because they did not pay enough attention to this people aspect. Now, inspections are expensive. It is shocking when you do the math, just how expensive an inspection is. A good recommendation, this number, it's like a universal constant, like the speed of light. Everyone who studies it seems to come up with something pretty close to the same number. Inspect about 200 lines of code per hour. That's not much. So 1,000 lines is going to take 5 hours for one person. If you have 3 inspectors, that's 15 hours of time. Very expensive. So if your inspections aren't really being effective, you're going to quickly decide that these aren't worth doing at all. It's one of those situations where if it's worth doing well. And if it's not worth doing well, we won't do them at all. I've seen many inspection programs fail because of that. Now, the cost of inspections is very visible. You can see when you have 5 people in a room doing inspections, you know where that time is going. What about the savings? How are the savings made visible? Well, if you are taking some data, you can see that. But without carefully looking back at the data, you have cost here, savings down the road. What do you think most managers are going to choose? Under pressure, when schedule is at issue, when they have to get that product out the door. You've separated the cost and the benefit in time. That's a hard thing, and there's also a lot of research that shows that that's something that managers, even if they know better, specifically have a problem with. So, what do? You have to start measuring. Third step. We have to start measuring our process. At least a little bit. What kinds of things do we need to get? Well, we could measure how effective our inspections really are. Well, how do you know? Problem with inspection is, well, you don't really know how effective you are until you get through testing, right? Yeah, turns out there are some in-process things we can do. A lot of data about correlations with the size of the product you inspect at a block and the rate at which you do it. That doesn't guarantee anything, but we do know if you inspect too much too fast, it will not work. You have to take your time. Otherwise, you know it was a failure. Still doesn't guarantee success. What else could you do? Statistical methods. Any of you done Monte Carlo type programming? Monte Carlo methods? Capture, recapture, game management. We'll borrow a technique that they've used. Mark and recapture. If you have multiple inspectors, you can actually use the different finds from the different inspectors to estimate the total number of defects in the product. For example, some group of inspectors, inspector group of inspectors, have taken a sample. How many fish are in this bowl? They've taken a sample of fish. They reached in with a net, took out some fish, counted them, put them back. And they found 7. We have another inspector go in. That inspector finds these fish, finds 6 of them. But of the 6, 4 were already captured. So what this is telling you partly is the more inspectors you have, the diminishing returns, because they're going to be finding defects that were already found. But what it also does is it gives you a statistical trick. Now, I promise I put this slide together, then I decided I better do the math at the end to make sure it worked. And I promise this is the only math we'll do in this presentation. If you want to do more math, come back for the tutorial on Wednesday. First capture, 7. Second capture, 6. 42. Caught both times, 4. 42 divided by 4. That's about 10. It really works. There's statistical variation in that, and I've actually run some simulations so that I can characterize it for different sizes. But you can measure the effectiveness as you go. Partial measurement. After you're done, well, this is where the real selling comes in. You can actually measure the actual yields. How effective were we really? You can look at the rates. You can compare the time in test and inspection. How much time did we spend in inspection? How much effort did we spend testing and fixing these defects? And if you're really good at this, you can look at how much rework are we getting back from the field. Now, have any of you built fairly large products where you've had to put them into some kind of formal QA testing? No, I don't see a whole lot today. A number of examples that we've worked with putting substantial products into test. How long do you think testing time, if there were no defects, would take on an entire project? Well, let's ask you this. How much time do you think final testing, like QA phase testing, takes on normal projects? Industry normal. A very good number would be about 30%, very good. 40% is pretty normal. 50% is common enough. I have seen it higher. If you know nothing else about a product, you know that it's gone into QA, how long is it going to be there? How long did it take to get there? That's how much longer you have till you can ship. Well, with this kind of testing approach, we have seen significantly sized products go in with few or even no defects. You can get the testing time down to about 5%. We typically see a range of 5 to 15%. But now you have a lot of information, you have a lot of knowledge. Now you're starting to see the next level of problems. We might still be getting too many types of defects into test or production, but they weren't implementation defects. We've got problems in our requirements, or we've got problems in our design. Maybe our test dates still are too variable. And you know what? Inspections are not easy to do. If you have 5 inspectors, do you think they're all going to be inspecting with the same amount of effectiveness? Highly unlikely. From the data I've seen, we've got a lot of good inspectors who can find 50, 60% of defects. But for those, you'll still find others coming back. They might find 10, 20%. High variability in defect effectiveness. A lot of that is training. But there is high variability. Very high variability in component quality. I don't think it's entirely a Poisson type of effect where defects tend to cluster in a few components. There are other things going on. Maybe the developer had a bad day, maybe it wasn't properly designed, but you find that a lot of your defects cluster in a small number of components, sort of like the Pareto principle. Partial measurement starts to uncover all of this. So now you have all this guilty knowledge about, we've made all this progress, now look what we've learned about ourselves. It's actually a problem that you have to overcome. You have to realize how far you've come to get to this point. I've seen a number of teams despondent when they look at this data because now they say, we're just awful. Then you have to go back and show, well, no, you're not. Look where you started. Look where you are now. But you have a long way to go. You have more steps in the journey. You have to know things like all these defects, where are they getting into the system? How do they get in? How did we get here? What do we do next? So to find that out, let's take another step. Personal quality ownership. Now, the personal ownership, the concept of personal ownership is that I, as a developer, take personal responsibility for the products I produce and how I do it. I am going to behave professionally. If not me, then who? If not now, then when? the team is responsible for all the components of the system. This is a team responsibility. But the individual is responsible to the team to follow a process and responsible for the quality of the products they give to the rest of the team. Use disciplined personal methods. Treat every personal review as a certification that the product is free of defects. In our PSP-TSP team, we use personal reviews in addition to inspections. Now, occasionally I see personal reviews in other areas, but other methods don't seem to put the kind of emphasis on the personal review before going into inspection. We consider this to be essential. It's a critical part of the process. Now, as defects are found, as you find your personal review defects, as you find them in inspections and tests, you find and fix those defects, and you try to figure out how you might improve to avoid them in the future. So partial measurement is, I'm sorry, that was the wrong one. Partial measurement begins the feedback loop. What we're doing with the personal ownership is starting to identify, oh, I think I got that one out of place, sorry. Yeah. Sorry, that too many changes in my slides last night. That went on the previous one. Let me jump ahead. Personal ownership. I'm going to come back to the medical industry. The checklist. How many of you have used a checklist? Any of you fly an airplane? Yeah? The checklist was invented essentially by Boeing back in the 1930s when their B-17 bomber crashed during a trial. They were actually showing it to the, I think then it was the Department of War. But it crashed. It was just too complicated to fly. So they invented this checklist to make sure that all of the things that you had to do to fly this plane safely were actually done. And this concept has carried over repeatedly. We use it in software. Dr. Pranovo at Johns Hopkins applied this to medicine. Central line infections. They know that's where they put a needle in a main artery. Infections were a very common problem, a defect. They found that at least one step was skipped. There are really just 5 steps in the process. At least one was skipped in more than 1/3 of the patients. How does that happen? Well, if you're in a busy environment, how easy is it to be distracted and forget to do something? Their use of the checklist is probably closer to what I would call a script, a process script. But it's very similar to the pilot's checklist. Have I done this? I don't move on until I've made sure that I've done this. Well, they put together a checklist and simply mark the boxes. Have I done step 1, 2, 3, 4, 5? Well, their infections dropped to 2 in 2 years. They almost disappeared. It's not a fluke. They started applying this in surgery. In the U.S., 150,000 deaths follow surgery every year. That is 3 times, close to 4 times the number of people who die in auto accidents. This is really a very serious problem. And if this is a problem in the U.S., consider what it must be in much of the other less developed parts of the world. Well, the central line infections were actually killing almost half of these. I'm sorry, they affected half of these people, and 5 to 28% of the time it would be fatal. Come the checklist. Atul Gawande wrote a wonderful book, a very good popularization called The Checklist Manifesto. There are a lot of things in that book beyond the checklist, so I really do recommend reading it. It's a very good book about process. You can see some ties to agility, where he worked with the building companies. He took the checklist idea to the World Health Organization as a low-cost, inexpensive way of making surgery safer in less developed parts of the world. Developed a safe surgery checklist. Now, his first efforts here were a failure. When you start making a list of things to do, it's a very natural tendency to put down everything you think you need to do on that checklist. And guess what you've just done? You've made it unusable. too cumbersome. So the key was this has to work in time-critical situations. If you are a pilot and you get into icy weather, you don't want to go through a long list. You need to go to what are the most essential things that I must do right now. So it has to work in time-critical situations. It has to be compact. Keep it short and simple. Only include the steps that are sometimes forgotten. If you never miss a step, don't bother putting it on your checklist. Only get the critical things. By critical, I mean the things that are likely to be missed. And the results were without checklist, with checklist, surgeries, complications, infections, and deaths. Complications, infections, and deaths went down by almost a factor of 2. So this works in other domains. It works for pilots. It works for doctors. Why shouldn't it work for us and software developers? Well, we suggest that it does. And that's part of following a disciplined practice. What are the things to put a good product into the field that you need to do? Have you really done all of them? Are you sure you haven't skipped a step? How do you know? You go back to your process script or checklist to make sure you've actually done them. So, personal quality ownership, you take control of the work. Use sound methods. Whatever those are, whatever your current methods are, use them. Really use them. Define and follow a set of steps repeatedly. Yes, I know this is a creative process, but there are a lot of things we have to do. So do the things that you need to do repeatedly. Do it consistently. Don't cut corners. Review your work after you're done. Do a careful review of your work before you put it into an inspection. I don't have the slide here, but it is quite true. If you put defects into a product, trivial defects, like spelling defects, obvious wrong words, people will find them. And they will miss the more important defects like the structure of the paragraph or the thinking that went into it. I've told people, and I've actually shown them this, that you can guide a presentation sometimes by putting a strategic defect on it. People will, like a laser, find that trivial defect and completely gloss over something else. Learn from your mistakes. When you find defects in your work, we're going to talk a little bit later about how you can take that back into your process and improve. So use these tools. Now you have a foundation. At this point, you can work consistently. You know what you're doing. You have a list. But that brings up the next set of problems. Now, first I want to take a short break because this has been going on a bit. Let's see if the sound comes up. This one has been, this one has been a little slow. Okay, it's starting. Anyone recognize this? Most of you probably aren't old enough. I was not quite 9 years old. It's not coming through. Roger, 1201 alarm. 2001 alarm. Bravo 1, Roger. We're go. This is the Apollo 11 lunar lander. They can see the moon. They are almost there. They got a 1201 alarm. Do you know what 12 alarm means? It means the guidance system crashed. That's not good. Primary guidance computer failure. But it's not a disaster. Why? Because they practiced this. They had the simulator, and they found 1201 alarms in the simulator. There are several things that could cause it. I think in this case it was they were getting some reflections back from part of their radar system that was overloading the system and caught. But they found that it would reboot itself in about 8 seconds. So they decided that rather than redo the software, which was pretty risky at the time because they didn't think they could implement and build new software that was sufficiently bug-free to trust, they'd rather live with the bugs they knew. So they waited it out, and they had a list of the power descent will be terminated for these bugs and for these codes. And you notice the 1201 isn't here. The 1201 had the wait list. Does it come back? Now, they had practiced this in the simulator. They knew it was coming. They followed their process. A lot of discipline. 8 seconds, mission control consistently demonstrated this form of competence. Now let's do a contrast. Teamwork, preparedness. Contrast this with what happened in the THERAC. In the THERAC, they didn't have independent reviews of the software. In the THERAC, they didn't consider the design of the software and how it would produce these specific types of failure modes. When the system had a problem, it just said malfunction with no description. They didn't know what the malfunction was. And what had in fact happened several times was they would just go right past the malfunction and keep on going. The Apollo program in the 60s really nailed a lot of this process stuff. And 15, 20 years later, in developing the THERAC, they missed it. Equipment control synchronization, all this was missed during the testing. Very different types of behavior with very different results. So, we have the process, we have these steps, we're acting disciplined. Well, how do we get better? Maybe my process was too complex. Maybe it's just too many steps, too complicated. If I change it, how do I know it worked better? Now here's a problem. I can make a change, but remember what Deming said about tampering? Just tampering with the system? How do you know it's getting better if you don't measure it? Well, the real effect of changes cannot be quantified unless you have a framework relating the defect introduction and removal rates across the life cycle. That has a lot of implications for what you need to measure to get to the next level. To get better, you need to choose achievable targets. Challenging but achievable is the sort of thing that comes up again in learning models like deliberate practice. So a few things that are typically seen in improvement in learning are you want to focus on your process at least as much on the outcome. Outcomes are important, but they don't happen by accident. You need feedback that is objective. For example, an external expert providing comment, or measured numbers. The stopwatch doesn't lie. You need it to be meaningful in that it relates the steps to results. You want it to be precise. That is, it has to be specific and enactable. What am I going to do differently? And you want to have feedback that is timely. That is, you want the feedback as near as possible to when you actually perform the work. Otherwise, we as humans don't learn it very well. So what you're essentially doing is you have inputs to some process, some outputs, and all this going on in the middle. We want to uncover this hidden layer. What are you really doing? Provide feedback loops, not just from the output to the input, but from the output to all those steps in the middle. When I do something differently here, how does that affect what I'm going to do differently? Characterize what happens inside, measure that hidden part of the process. And that takes us to the next level, step 5. That's 5 of 8, so we're getting there. Understand the work. Quality is no accident. It happens from intent. So, when you measure your performance, what are the kinds of things you can measure? Well, how much product am I delivering? So you need some way of characterizing your product. What are the dates? How long does this really take me? What are the steps I'm doing along the way? How much time do I spend in each step? How do I measure quality at each of these steps? How many defects do I produce along the way? I can show you some defect data that you simply wouldn't believe. I'm not going to make this a data presentation, but I can show teams and organizations that know, along with their process, how many defects they're going to inject in any part of the system, because they have data that shows that's what they do. How do they get rid of them? They know what they do to get rid of them and where they're going to find them. With shocking regularity, with shocking precision, they know where they are injecting defects and what they have to do to remove them. What kind of defects are they? Jorge Santillana. Those who forget history are doomed to repeat it. We are recording the history. Use the personal data to benchmark. Benchmark your performance and use it as a basis for improving your performance. You want to characterize and analyze current performance. Try to make the analytic and causal relationships between what I'm doing and what the results are. Generate improvement proposals. What can I do differently? Set your performance goals. What do I want to achieve? You want to select proposals that are likely to get you to your objectives. Implement the proposals. Gather more data and evaluate the results. Did it work? What did I want to accomplish? What did I change? Did I actually implement it properly? Did I get the results I want? That is how we do personal process improvement in our PSP. And those are the same steps, by the way, that you see carried out in a lot of learning paradigms. There's really nothing new there. So the results, you can often reduce up to 75% of the defect escapes just by putting in personal process discipline. Typically, there's no loss of productivity through a unit test. Might be a little bit delayed in the unit test, but you see enormous cost savings downstream. That is, even if putting in the inspection, say, takes longer through a unit test, you will save that before you get through integration or system test. Partial measurement, personal measurement, still not enough. We're measuring our process, but what are we really doing? I can repeatedly get these results. Well, good for me. How do I get even better? Well, we can try to change our process. Maybe it's too complicated. Do something differently. So let's take just a brief check of where we are. High quality requires disciplined individuals and disciplined teams. Process, how you do the work, governs the quality of the output. Complex work must be guided, or you will skip steps. So any complex work needs some sort of systematic guide, like your process scripts, your checklists. You have to measure and manage. That's a requirement for managing the process. It's a requirement to learn. You need to trust the data. The data, if you're taking good quality data, it's not lying to you. Don't rationalize the data away. Act on it. Now, utility, which I will define in a minute, can be achieved at lower cost. So let's go to our next level. Design. Design has been, in our view, underemphasized in the past couple of decades. It's starting to make a comeback now. And it's always sort of been there, but not in the way that we envision. Who remembers these? Anyone used one of these? I had one of these before the TI-20 was the first $20 calculator. I had one of these before I got a TI-20 in 1976, I think. What did you have to do? What are some of the things you had to do to use a slide rule successfully? Anyone, how many of you have used a slide rule?
Just a bit.
Just a bit, okay. Well, let's jump ahead. What does it not give you? It gives you like 3 or 4 significant figures. It doesn't tell you where the decimal point goes. You can use this for multiplication, division. You can do square, cube, roots. It doesn't tell you where the decimal point is. You had to be able to figure out in your head, before you use the slide rule, at least a scale of what the answer should be. Now, I've used some modern software codes where you can do that, but they can do so many remarkable things now, I can't even begin to guess at what the number should be until I push the button. John Wheeler, the famous physicist, had a rule that he told his students: never make a calculation unless you already know the answer. Don't trust the machines to do your thinking for you. Well, that's not that you would have to get a precise answer. You can use the machines to get a precise, but you want to have some intellectual grasp of what's going on. Try to use simpler methods, simpler models to get an approximation. And then you can use the new tools for more precise answers, but you validated those with alternative, simpler forms of calculations. That'll give you a less precise but an approximate answer. There's a lot of design in that. And it's drilling from one level of abstraction to the next. That Saturn rocket that was used for the trip to the moon was designed by engineers using slide rules. Oh, there were some computers along the way, but they were pretty expensive and they weren't very big at the time. So design. Very simple example of design. Cajero, do you call them Cajero Automático in Uruguay? Okay. That's what they are in Mexico. This is a representation of a state diagram. Most of you have studied state diagrams, I hope. Very powerful technique. State diagrams are very useful because they abstract one aspect of the system in a way that is very easy for us to visualize. What they do is design allows us to contain complexity. Now, I don't know why these things find me. I found a defect in an automatic teller machine, a Cajero Automático. I accidentally typed in a leading digit in the dollar field, and the machine got stuck. It took me 5 minutes to get it into an exit mode. How do I find these things? I don't know. How do they find me? But the point is, there are plenty of techniques that have been around for a long time that you can use to reason about different parts of the system. There are a number of different techniques. You use different techniques at different levels of abstraction, at the system level, at the component level. Some of these are represented in unified markup languages, unified modeling language. I still find the state diagram and the flow chart to be the most useful for me. But the concept is, design is the creative part of the software development process. That's where the really interesting thing is. We give a lot of students a problem, and the first thing they want to do is start taking out the laptop and start typing in the answer. Now, a true story. We were teaching a personal software process course a few years ago, and one of the students was the only one who didn't open his laptop. This was a professor from Australia. And then about an hour later, he opened up his laptop and started typing in code. Guess who the first one to finish was? Because he had thought about the design of the program. What are the inputs and outputs? What does it have to do? Understand the requirements, go through the different scenarios, sort of like use cases. Are there any questions of state? Are there any potential places where I could get trapped in state? Any edge conditions that will show up as not being connected? Are there states I can't get into or can't get out of? He broke it in, assigned the functionality of the components. By the time he got to writing the code almost wrote itself. It was automatic. He had separated the creative part of the process from the routine part. And it turns out code Software code, be it Fortran, Java, C, is a very poor design representation. It does not allow you to abstract away these concepts. And you tend to make a lot more defects writing if you do your design while you do your code. So, design techniques. Use appropriate design techniques for your domain, and you will inject fewer defects. And you get some bonuses. Let's see. Oh, I already went through those. You get some bonuses. You manage complexity. By and large, components are smaller. What does smaller mean? Oh, if it's fewer lines of code, there are probably fewer defects just from that. You get to reason about the system before I build it. Imagine I can actually reason about the system. I don't have to rely on tests to tell me it works. I can rely on tests to make sure that I did everything right. And if you do a formal design, that's actually reviewable. You can create artifacts that can be inspected by others. And we find an enormous amount of benefit to this in the architecture world, in the software architecture, where you can reason about very important properties of the system, like speed and throughput, before you start writing code. See how I'm doing here? Let's see. I think I'm going to make it. So, what could go wrong? Another video. I don't think you can hear this, but you can see this. This is the Ariane 5 countdown. You are about to see a software defect. Okay, give it a minute. I know this won't be more than another 30 seconds or so. Wait for it. There it goes. There went $7 billion of development and a $500 million payload.
1994?
Yeah, somewhere like that, yes. So, what happened? You know, of course they designed that thing. Well, I'm going to oversimplify. I'm not going to go into a case study of what happened in Ariane. I will admittedly oversimplify the problem, but essentially what happened was there was a failure in the software in the inertial guidance system. What happened? They tried to pack a 64-bit float into a 16-bit signed integer. The problem was it overflowed. It was going too fast. They didn't think the velocity in the software, they didn't think the velocity would ever be that high. Why? The code was originally written for the Ariane 4. Why do you think they had an Ariane 5? Bigger and faster. So here was a good example of a failure because of reuse. It worked perfectly fine in the initial, but it did not have the necessary properties to be reused in the Ariane 5 without modification. That's unfortunately not an isolated instance. I've seen similar types of examples with things like the Patriot missiles. Reuse of software can be a problem if you don't have really well documented what are the implicit limits in the software. This is buried deep in the implementation. Now, it gets more absurd. Okay, the calculation containing the bug, that shut down the guidance system, that confused the onboard computer, that forced the rocket off course, and when it went off course, it blew itself up, it destructed. It didn't serve any purpose. It was used to align before the launch. Why was it still on? Because in a previous version, someone thought it would be a good idea to leave that on for about 40 seconds so that if they had delays in the launch, they could reset the guidance and keep the launch going. That blew up at 36 seconds. You can't make this stuff up. Okay. Roger McCarthy was from NASA, and he talked about failure that was fairly bought. When you're pushing the edge of technology, you're going to make some mistakes. You're trying to do things you never did before. You're going to have failures. That's just the nature. But you should not be failing on the routine things. The routine failures are going to prevent you from learning what's going on here. So what are the kinds of problems you could have? Low yield, using informal rather than formal inspections. Maybe you're just going to inspect critical code. How many of you have heard of just inspecting the most important code? I always ask, okay, you know what is the important code. Which code is not important? If it's not important, why did you write it? The key lesson is that it's hard to know how that defect might propagate. It's very hard to contain. So you might be putting defective code back in the test. You have to learn to anticipate failure, and that's where we get to the next couple of steps. And I can see that, well, I'm running short on time, so I'm going to go through the next pretty quickly. Defect prevention. Using design and defect prevention, thinking about what can go wrong. You don't just design. Don't just design to get it right. Design so that it cannot fail. Fail-safe, pokey-okey, all useful concepts. To get here, you have to have a very strong foundation. It's still not enough. User-based measurement. So let me flip through some of these pretty quickly. Software architecture. If I look at two of the technologies I've been working with at the SEI, the PSP, TSP is focused on the implementation phases. Software architecture is focused on the early design. And they really do fit together very well. Building the right thing, I'm going to skip this one example, but it's about understanding what the user's needs really are. What does quality look like to the user? And then, if you understand what the quality looks like to the user, we can now apply everything we've learned in these steps 1 through 7 to making the product right. So this example was base to the moon. You go to the moon, return safely to Earth. They finally got out of customs a couple of weeks later. In our world, what does it mean? Building it right. It means understanding the needs, engineering the process so that it satisfies all the customer's needs, then build it correctly the first time. So I'll wrap this up with a quick discussion of an example from a couple of years ago. Are any of you familiar with the stock exchange in Mexico? They rewrote this software last year. It was a big project. They came to the SEI, and they engaged the software architects for help with the early life cycle issues, and our TSP team for the implementation and building. It was the first opportunity we had to work directly with our architecture team. Previously, they'd been working here, we'd been working here. Well, this was really getting to a level 8 type of situation where we took the teams through all 8 of these steps, but we did it in a very compressed format. Versatech had a set of requirements, very, very demanding. What does it look like? Well, they had to have high throughput, 1,000 threads per second, scalability. They had to be able to switch on the trading engines, the servers hot. How long? Modifiability. Rules change all the time. Legal requirements change all the time. They had to be able to make changes and get them tested and into production fast. Goals? By designing the system properly, by understanding what the needs were early, going through the proper design, and then building it right the first time, they had a goal of a millisecond latency. Beat that by more than a factor of 10. Testability, they can turn around a test in an hour. just remarkable performance. This is what you can actually achieve getting up to level 8, based on real user requirements, satisfying the user needs. But underneath those user needs, they don't care how you did it. But you have to be able to go through all those other steps in the quality so that when you build the product, you are not only building it to their specifications, but it is going to work. And in the case of Bursatech, we spent about 12% of the total budget in the architectural phase. Spent about the same amount in the testing phase. They were done months ahead of schedule. They put in a very soft schedule because they were worried about overruns. They were waiting on everyone else. So, doing it right the first time, they produced a first-rate product. This is very possibly the best trading engine in the world now. They did a terrific job. They did it, by the way, with several senior developers doing the architecture, a number of junior and very modest experienced software developers. This was not a team of superstars. They had some very good people, but there were a lot of good but ordinary software developers doing this work. This is what ordinary people are capable of doing. You don't need to have the best. If you follow the discipline, everyone can be good. No accident. These are the process phases that they defined. How much time did they expect to spend in these phases? How much did they really spend? The blue is plan, the magenta is actual. They knew where their time was going to go. They planned their work. They followed their plan. So, let's wrap this up. The call is to strive for excellence. Devote yourself to excellence, and you might achieve it. It'll be worth the trip. Devoting yourself to excellence means personal discipline. It means applying some measurement. It means putting in some effort, but it is worth it. I'm not going to go over all the definitions of software engineering. We might quibble about some of the specifics, but I think we all agree that software engineering is drawing on computing and mathematical foundations to develop models and reliable techniques for producing high-quality software. That's what engineering is all about. So our mission, lead by examples. As professionals, as educators, guide others down these paths. All begins with one step. Thank you. Now, I say I took up all my allotted time. Yes.
Okay. What do you see as the main problem? What do you see as? What do you see as the main problem of the variation in different areas, for instance, inspection, measurement, the variation in result, in effectiveness of results? Is there a lack of a real background in professionals, a common, a standard background? Because human resources are the key success factor for processes and for
Let me try to paraphrase your question and make sure I understood it correctly. What are the real problems behind ineffectiveness in process and inspections? I see two major problems. One of them is we haven't really trained most of our software engineers properly. It's rare that we have them trained in how to do formal inspections. We typically give them exercises and they're judged on how the problem came out at the end. Well, a lot of learning theories suggest that you have to focus on the process steps at least as much as the outcome if you want them to really achieve mastery. But there's a second problem, and that is it's a management issue. It persists because management accepts it. If management demands excellence, people are actually very accommodating. They will do what their managers think they want them to do. And if they hear speed, 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 get this out the door fast, 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 they're going to behave like that.
Hard to resolve then.
Yes, it's hard to resolve, but it can be done. It won't happen overnight, but there are companies out there that are taking this quality message and are being very successful with it. So my vision is that, maybe when I'm old, I'll have a cell phone that works all the time. Question.
Yes, Bill, thanks for your work. I am Oscar Castro from University Polytechnic of Valencia in Spain. We have been working in quality for a long time, and we feel somewhat frustrated because it seems that when we are saying and presenting the problem, we are always saying the same. It seems that the problem is clearly stated by the progress of the community, doesn't look like to be really successful. So you point out the points clearly, and I have at least a couple of comments that I would like to know your opinion.
I'd love to talk about them. We could do it now or offline. I see there might be a couple other questions. Up to you.
Yeah, it's a question.
Okay.
So my question, one of them is, would you talk about the interrelation between product and process? That is very important. My question is, does the concrete process affect strongly the techniques that should be used for inspecting? Because when we talk about inspection, sometimes it seems that we talk in a general way. But depending on if you are doing modeling, requirements engineering, programming, it seems that the inspection techniques are completely different. Is that true?
The actual inspection is very different for things like design and code. For code, it's really more a matter of having a list of things that you're looking for in the code that are common problems. But in design, it's a much harder piece of work. In design, you have to actually do an analytical assessment. So you need representations that capture the abstract concepts, and so that you can reason about them. There are design verification techniques that are much closer to working out a math problem than actually doing a code assessment. So yeah, yes. The answer is yes. The specific techniques that you have to apply in evaluating designs and requirements are very different than code.
And the other question is, why are the results of inspection and the results of measuring quality so different depending on the domain? I mean that, for instance, in critical systems as avionics or so on, really the reliability of software is quite high, while in what we call organizational database system, normally we accept flaws and there are plenty of problems. So why some parts of the domain, in some domains testing is so good, while in others is so bad?
I can only speculate, but I see two main drivers. One are legal drivers. In areas like avionics and medical devices, there are legal requirements that they must satisfy. Now, just following those legal requirements doesn't mean that you're going to do it right. But they also have liability. So let's take this to another domain completely, where the legal requirements are off the table. Video games. How many of you play video games? How many of you see lots of flaws in the video games that they distribute on DVDs? Some? Yeah. Some more than others, but overall, video games tend to be one of the more reliable types of software you can buy. We work with a video game company. The truth is, they have to pay liquidated damages for defects, the developers. But they get royalty points on the games. They make their money by selling copies of the game. Every defect, they lose royalty points. So it comes right out of their pocket if there are defects. So the economic drivers, I think, are brought home. It's not just, it just seems to be part of the human condition that if you have a separation between the causes and effects, even if you know what to do. I saw an article in Harvard Business Review that did a study on it. people still, even if they know the right answer, they often go down the wrong path. Not everyone. Some people get it. But it is frustrating. It seems to be part of the way people work. Yes?
Just a follow-up on this, and ask a question from the University. So from what you just commented, the drive really is the legal and the liability point of view.
There's a big drive in legal liability. I know we work with a couple medical device companies, and it's not just the legal liability, but because of the legal rules for releasing products. If there are defects in the product, they have to go through a very expensive recertification process, even if the defects aren't safety critical.
That leads us to another issue, which is the cultural thing.
Yeah.
Because, I mean, I don't know if you agree with it, but the industry is so sloppy against the current practice. I hope I don't offend anyone here. Okay, but in order to have let's say a big change in this, I mean, we need to change the culture and let those with us, I mean, the ones that are.
Okay. Well, let me answer you this way. The question had to do with the quality of industry and what people are willing to accept. There seems to be some research suggesting that when people are working on some kind of learning process to achieve certain levels of mastery, you will achieve a certain amount of success. And humans appear to be, by their nature, capable of achieving a certain amount of success and just being satisfied with it. That's how we learn. The people who go to the next level, and I described here 8 different levels that you could possibly go through. The people who go to the levels of real mastery apply a different set of techniques. So I'm saying what we see in industry is really human nature. But for all the human nature, we still see in the Olympics those sprinters who try to be the fastest. They do things differently. I think we know what those things are, and normal people can apply them and be a lot better. How to get them to do that? Well, we have seen it done when management and the culture ask for it.
The point is they don't call themselves engineers as we do.
Yes, well, sometimes they do, but in the United States, in some jurisdictions, they are not permitted to call themselves engineers because they do not meet engineering standards. I think the state of Texas is an exception. Okay, we're over. Okay, well, thank you.